Hi everyone. Today's seminar is on experimental analysis of multi-static, multiband radar signatures of wind turbines, which is joint work that myself and Matt have been doing in the past few months with Alessio in Cranfield. That's the content of the presentation. So at the beginning, a few words on the general problem of wind turbines and radar systems coexisting together. Then description of the experimental work that we have been doing and some results, and finally conclusions and ideas for future work. First of all, some numbers. So to give a sort of context, basically the UK has a goal to generate 15% of energy from renewable sources by 2020. And onshore and offshore wind farms are expected to contribute greatly to the achievement of this objective. Some numbers provided by the industry consortium of which is called Renewable UK, so basically manufacturers of wind turbines, wind farms, with solar plants, says that basically the stored capacity last year produced about 17 terawatt hours, which means basically electricity for about 4 million average households, or a single turbine, like an average size turbine, 2.5 megawatt, can generate electricity for about 1,400 houses in a year, or run an average PC for over 2,000 years, or I don't know how they measure that, but they claim making 230 million cups of tea. The problem is that basically wind farms cause interference with radar systems used for air traffic control, for the defense and surveillance of the airspace, and also for radar that are used for weather forecasts. The main mechanisms, so to say, for this interference is the fact that the turbines have, of course, a very large radar cross-section, talking about objects which have got a tower which is approximately 50 meters tall, and blades which are in the order of 30 or even more meters long. So these were some numbers from a paper in 2007 that calculated that the radar cross-section is on the order of 55 dBSM against 10, or between 0 and 10 for a small fighter. And the other problem is, of course, that the wind turbines are rotating, and depending on the wind speed and the angle, and the aspect angle of the turbine to the radar, the tips of the blade can produce Doppler shifts which are comparable to those produced by aircraft or helicopters. So the general adverse effects include the fact that there are false alarms, that the radar has got some kind of reduced performance in terms of detection capability of target in the area nearby the turbines, and the loss of tracks. As a result of that, the potential development of wind farms is blocked. This was another number produced by the industry. About 12 gigawatt of capacity was objected in 2013 with objections from either the MOD or the Civil Aviation Authority. Now, there are some techniques that have been proposed, and the CIA itself sums them up in this document. So some of the mitigation techniques are on the side of the wind farm. The easiest one is relocate the wind farm, putting it somewhere else, or rearrange the position of single turbines within the wind farm, or put some kind of terrain shadowing, so if possible having some kind of artificial hill or something that screens the turbine from the radar. But also things on the design of the wind turbine itself, so for instance introducing some radar absorbing material on parts of the turbine, or changing the design of the turbine itself rather than having the classic horizontal axis of rotation, having some kind of vertical axis turbine or wind lens and some other design. All of this is possible, but there are costs associated with it, and of course sometimes all these things make the wind farm not profitable, so at the end the developer doesn't build it. Other approach, of course, goes to modify the radar, so we can have modifications on the antenna beams and on the pattern to try to separate the unwanted clutter from the target. All possible improvements on the detection and tracking algorithms to try and separate the wind farm contribution from the target contribution, and also the so-called in-field radar, which is basically an extra sensor that complements the coverage of the primary radar, and this goes towards a sort of multi-sensor / multi-static scenario. Coming to our work, we have been collecting data in 2 different trials in January and in May 2015, using at the same time NetRad and CW radar at X-band that Alessio has got. So the data that we collected are multi-static, 2 different bands, and also 2 different polarization, VV and HH. This is a figure of the wind turbine here. Maybe I don't know if you can see, but there are 5 turbines, and we were located here at this site. There is like a small country road here on this site. The first trial that we did in January, we set up NetRad only with 50 meters baseline, and unfortunately there would be another turbine here, but that day it wasn't rotating, so we were forced to use the sort of second turbine, which is this one, and the bistatic angle was quite limited, about 6 degrees. In May, we did another test with 100 meters baseline, so 3 NetRad nodes and 2 Alessio's radar deployed here and here. And the first turbine this time was rotating, so the bistatic angle is larger and approximately 23 degrees for this combination of nodes. And I think
what's the plane of rotation of the turbine with respect to the radar look direction?
That's
so
one.
Is it going like that or like that?
I think at the beginning of the experiment it was sort of maximum Doppler, so completely perpendicularly, but it's changing so abruptly, and there's no way to sort of measure or predict it unless the company that owns the wind turbine tells you, because they record that information. So that's one of the biggest limitations, not being able to, unless visually filming when you're measuring.
Well, that's what I was going to suggest.
Yeah, we collected some videos, but it's difficult to say the exact angle. That's the wind turbine, is approximately here near Swindon, Oxford, near the Defence Academy in the UK. It's made of 5 turbines, and it's been operational since 2008. The size of the turbine is approximately, as I was saying, 50 meters tall, and each blade is approximately 30 meters tall. These are the 2 radar systems. NetRad, I think everyone knows these parameters now. And this is the CW radar that Alessio has, it's 10 gigahertz, and uses 4 antennas. This is not, strictly speaking, a multi-static radar. It were actually 2 different monostatic radar deployed at the 2 NetRad nodes, operating simultaneously, plus minus some delay in clicking to say start recording. These are some results. We looked at the Micro-Doppler signature using short-time Fourier transform of a single turbine. These data are at S-band, so are NetRad data. Here we got monostatic, node 3, and node 1 it was the middle node, so approximately bistatic angle 11 degrees. And this was at the farthest node approximately 23 degrees of bistatic angle. This is B-pole, this is H-pole. One other caveat on the data collection process is that these VV data and these HH data are not simultaneous, because as probably people who came to NetRad trials know, it takes some time to change the polarization of the antenna. The antenna needs to be manually rotated, so they are not simultaneous. There were actually sort of maybe half an hour difference of time between the data set. Empirically, we can see some difference between, if we look, I don't know, at this Micro-Doppler signature and this one, it might look like the overall bandwidth here is smaller, and here perhaps where compared with that. And also that the reflection, positive and negative Doppler shift changes with polarization. One of the things that we tend to observe is that it's more intense, the signature at HH for negative Doppler rather than positive. At X-band, the radar is CW, so all the contribution from different turbines basically falls in the same in the same Micro-Doppler signature. Again, we have BB data and HH data. Node 3 was the node placed at our neutral monostatic node, and this was placed at the bistatic node. Again, different nodes see sort of quite different Micro-Doppler signatures. Sometimes there is quite a big difference in terms even of the intensity. But these are all sort of empirical observations, which we would like to sort of go over them using quantitative comparison, so having some parameters that allow us to do a comparison. We use the centroid of the Micro-Doppler signature and the bandwidth around the centroid. These are some examples. Again, BB pole and HH pole, mono and bi compared on the same figure. Here on the left-hand side is the centroid, here is the bandwidth. We can see that the peak of the centroid is slightly higher for the monostatic. Here not much, but here it's more evident. But then, if you look at the bandwidth, we got kind of opposite situation, where for the VV pole we had the larger bandwidth at the bistatic, and for the HH pole the larger bandwidth at the monostatic. Another parameter that we try to look at is the average of the average intensity of the Micro-Doppler signature across the set of Doppler beams. So we selected 100 Doppler beams, we average them, and look at the peaks of the Micro-Doppler signature on the average. Here we have two examples of BB pole between 200 and 300 Hertz and between 600 and 700 Hertz, so positive Doppler shift. Here the monostatic peak seems to be higher than the bistatic in both situations, but I'm just showing basically the best results because it's not always so clear. There are situations where it's true the opposite, where the bistatic is higher, and this depends on all these parameters: the polarization, the bistatic angle, also which neutral node we are considering, and as Hugh was mentioning, the turbine aspect angle, on which we don't have much control. If we look at the same parameter X band, we get sort of similar situation. So if we look at the BB data, both the centroid and the bandwidth are sort of higher for the data node 3, which is co-located with our monostatic. And if we look at here at the HH data, we get sort of opposite situation where the data node 2 present a higher parameter. So there is no sort of unambiguous conclusion yet, apart from the fact that we think that the data are valuable because they are multiband, they are multistatic, and at two different poles. And we recently acquired dual pole antennas that probably will allow us to get simultaneous V and H next time that we go. And so this capability of collecting this data, we think, is still valuable, even if the conclusion in terms of data analysis is not so unambiguous yet. We saw that for some combination of these many parameters, there are geometries that seem to reduce the effect of this wind turbine clutter. Main parameters, as I was saying, is in fact the turbine aspect angle, which changes over time. Sometimes it changes even during the same recording, which was 10 seconds, because if the wind changes direction abruptly, the turbine will rotate to try to follow the wind. And another limiting factor in terms of geometry is the fact that Netrad was working in wired mode, so we have cables between the nodes, and we cannot have a baseline longer than 100 meters. Future work, we would like to collect additional data with different bistatic angles and geometries. Also move to longer recording, so we can go to a sort of statistical description of this clutter, trying to take into account on a longer recording how even the turbine is rotating. So rather than collecting many 10 seconds recording, making a long recording and trying to get a statistic out of it. Especially this is not much material published in terms of statistical description, maybe a few papers, and most of them not with experimental data, certainly not with multistatic experimental data. Another interesting thing could be to try to embed some target signatures on this cluster once we have maybe a longer recording and look at probability of detection and false alarm. Some other work which could be possible is having a sort of scale model of the wind turbine or simulations, but this kind of work, scale models and simulations, have been sort of extensively done by other people in the past. So going more towards experiments and statistical description is probably more novel than this last part. That's it. Thank you.